Hey folks, we're going to look at relative motion today. Relative motion is basically analyzing the motion of two or more objects that are moving at the same time that might have different velocities or accelerations. And so I made up a problem about me and my son. I chase after him a lot, and so he gets up to a pretty good speed, but because I have longer legs, I can catch up to him. And so that's kind of what this problem's based on. The diagram just kind of shows you it's a dot diagram of where we are in relative space each moment. And so each dot is, one time interval. Well, maybe we'll say it's like a tenth of a second or something. Um, and the idea is Jay is like running past me. I'm like standing there or sitting there, and he runs past me at like constant velocity and continues to move at constant velocity after he runs by me. Maybe there's something dangerous over there I don't want him to play with. So as soon as he gets past me, I like start to chase after him. And I chase after him with like some acceleration, and I keep accelerating until I like snatch him up, pick him up, and prevent him from doing whatever he wanted to do. That's kind of what this problem is based on. In relative motion, it's important to know where the objects start the problem relative to one another. And the way I've made this problem is to say that we start at the same location. The other thing you want to know is like, when does the problem end? And because I'm like chasing after my son, the problem ends when we get to the same location. So once I reach his location, wherever that is, that's when the problem ends. And then you also want to have an idea of like, do these two objects move for the same amount of time or different amounts of time? And I try to draw the diagram to show that it's the same amount of time. So first dot, second dot, third dot, fourth dot, fifth dot, sixth dot. This is going to take the same amount of time for both of us. And that's going to make the most straightforward question algebra-wise. If I changed up the amount of time each object had or the distance they covered, the problem would get more complicated. But this is really as far as we need to go in AP Physics 1. The facts I have is that J can run at 2.7 meters per second. I don't know that, but I made it up. And I can accelerate at 1.2 meters per second squared. And I start running as soon as he passes me. The way you want to approach a relative motion problem is to generate an equation that describes the location or velocity of an object over time and compare those whenever you have equivalent variables. So I'm going to do this for J first, and I'm going to use the position function equation. And I'm going to simplify it and say that we'll just say that x naught is a position of 0. And we'll also understand that because he's running at constant velocity, his acceleration is 0. And so the equation that describes like where J is at any moment in time is x equals 2.7 meters per second times time. So I have a relatively simple equation showing me where J is at any moment in time, and that's that. For me, I'm going to go the same way and use the same equation, x equals x naught plus vx naught times time plus 1/2 ax t squared. Now for me, we can also say that x naught is 0. And the thing that makes my motion different is that instead of having an acceleration of 0, I have an initial velocity of 0. So I'm just sitting there, and then I like notice him run by, and I start to chase. So my equation simplifies to x equals 1/2 1.2 meters per second squared times time squared. So I can write that as x equals 0.6 times time squared. So I have these two equations, and they each represent the location of one of us over time. And so for the majority of the time, the positions will be different if I plug in random times. The trick is, this problem is basically saying, how long does it take until we reach the same location, and then how far does J travel in that time? So what I want to recognize is the whole point of this problem is that I catch up to my son. So we get to the same location at the same time. And so that means that between these two equations, the x values are going to be the same only once, and the corresponding time values are going to be the same only once. Now, we do start the problem in the same location at the same time, but then only once do our functions overlap. And so where those functions cross one another is going to represent the answer to the problem. So the way I solve this, to solve it for time, it's a system of equations. I have two variables, or rather two equations and two unknowns. To solve for time first, I would set the two equations equal to one another. So for time, I would say 0.6 t squared equals 2.7 t. And so, that's a quadratic equation. And because it's quadratic, it has two solutions. You could factor out a t, and you would say, okay, well, one of those solutions is t equals 0 seconds. That's not our answer. We kind of already know that. If t equals 0, this is a valid equation, and that's just what happens here, that we start at the same location at the beginning of the problem. So I know that's a solution, but I don't need that. If I factor out a t, the equation becomes 0.6 t equals 2.7. And so I can now solve for the time. If I divide both sides by 0.6, my time equals 4.5 seconds. So the two solutions to this equation are t equals 0 and t equals 4.5 seconds. This is t equals 0, and then this is t equals 4.5 seconds. And so that's the first answer to my question of how long does it take me to catch him. To get distance, how far does J go before I catch him? I can use either equation. I'm just going to use this one because it's simpler, but we both travel the same distance in this problem, so I can use either one. So for distance, I just say x equals 2.7 meters per second times 4.5 seconds. And I get 12 meters. Okay, so 12 meters is how far Jay runs before I catch him, and given my acceleration and his initial velocity. So this is one example of a relative motion problem. We will look at them using graphs in class some other time, but this is about as complex as it's going to get for us in terms of like an algebraic equation. So that's one relative motion problem. And again, you always want to have the goal of making equations that have variables in common that you can then solve as a system of equations. And so that is that.